Hello, welcome to another lesson. In this lesson, we're going to be talking a little bit about circles. And when we talk about circles, we are going to be dealing with something called a radian. And so the first thing we should do is talk about what it means to have one radian. Let's look at the definition here. When the arc length S equals the radius R, the central angle, theta, is 1 radian. Now that might seem very confusing to you. Let me show you visually what a radian means. A radian can be demonstrated by this diagram here. We start with a radius, and just watch what happens. Okay, 1 radian is this angle. So let me talk it through this time. The radius of the circle, if we were to take that radius of the circle and make it equal to an arc length, which means bend it down, and that's the kind of a section of the circle or a section of the circumference, and then we know that that's the radius in both directions. That's the radius and the radius. If we go along that angle now is what we call 1 radian. So the thing about radians is that we really don't often think about its definition very often. The reason we want to talk about it right now is because we've been dealing with degrees, and it turns out that 180 degrees is a pi radians. And so it's about 3.14 and so on radians. So about that's half a circle. And so if we draw this out to try and get an understanding of this, we have our 0 degrees, our 90 degrees, our 180 degrees, our 270 degrees. It turns out that if 180 is pi radians, then at the start of 0, half of this would be 90 degrees, or in other words, that's pi over 2, and 270 would be pi over 2, 2 pi over 2, 3 pi over 2. But the most important ones by far are these conversions, or more specifically, this one right there. Oops, I shouldn't have wrote that. This one right here is the most important. It means that 180 equals pi. Why am I trying to get into this? Why am I explaining this so much? Well, because we're going to have to convert from degrees to radians, like I said. And one other thing I should have probably mentioned, technically 360 is 2 pi, because if 180 times 2 is 360, then pi times 2 is 2 pi. So we can see that these things are related. Let's move on to the next page. So this whole page is going to be about converting degrees to radians. And all we need to do is remember that this relationship is true. 1 pi radians is 180. So let me give you a little chart we can use to remind ourselves how to do this stuff. Okay, so that's going to be a little reminder of how to do it. If we have degrees, we multiply by pi over 180 to get radians. So in the first example here, it says change to radians, use 2 decimal places in your answers. So if we want to change 2 radians, we need to multiply by pi over 180. And I'll show you exactly why that is right now. So if we start with 56 degrees, think about your unit conversions. You want to change it into degrees, so you want to change it into radians. So we have pi radians on top and 180 degrees on bottom. So we're still multiplying by pi over 180. But the reason it works is that these degrees, the symbol, which means degrees, will be canceled and our final answer will be given. So if you calculate this out in your calculator, 56 times pi over 180, some calculators will give 14 pi over 45. That would be how many radians we're left with. Again, radians here, radians as our answer. But most calculators won't. And so it's perfectly fine if we just use round to the closest 2 decimal places. And so 0.98, and what is it? It's radians. Radians is our units here. So I'd like you to try the second one yourself. Pause the video and give it a shot. And in the meantime, I'll write it the answer and you can see if it makes sense to you. And there we have it. The reason it works is that degrees will cancel on top and bottom, leaving radians. And remember, if you're going to radians, you need to put the 180 on bottom. If you're going from radians, you put pi on bottom, or radians on bottom, which will cancel out. That's exactly what we're going to do in this case. So we're going to convert radians to degrees. If we want radians 2 degrees, you multiply, and you want to get degrees. So the degrees go on top, and it's the pi radians on bottom. So let me do the first one, and I'll leave the other two for you. We start with 0.256 radians. We want that in degrees. So put the radians on bottom. We right away know that that will cancel. And this will give us a degrees as our answer. That tiny little degree symbol is our sort of hint that we're going to get the right answer. It's on top, that's what we want. So that's 14.7 degrees. That's all there is to it for this question. I'd like you to pause the video and try B and C yourself, and then I'll write out the solution. So pause right now, and then I'll write the solution. So the first thing I'll do in this case is note that 3 over 2 is 1.5. So that's pretty important. That'll make our lives a little easier. So we have 1.5 pi radians times pi radians over 180 degrees. And the neat thing here is that radians will cancel, but pi will cancel as well. So that's really neat. If that doesn't work out for you, then you can actually convert it to you can convert 1.5 times pi into a decimal and just work it out that way. That'd be fine too. But in the end, we get 270 degrees, which actually shouldn't really be a surprise if you remember what I did at the very beginning. 270 degrees here, I said was 3 pi over 2. And so 3 pi over 2 is 3 over 2 pi. So this checks out. All right, the last one I'm not going to give any explanation. I'd just like you to try yourself. And there we go. All right, cool. Let's move on to the next topic here. In this topic, objective 3.2.4, we need to find the values of the trig functions of angles in radians. Okay, interesting. We haven't done this before. We've only found the values of trig functions of angles in degrees. So the most important thing is, in this case, if it's in radians, make sure your calculator is in radians. If you do that, putting this in is going to be super easy. I'd also like to add one thing here, one little extra piece of advice, and that's if you see pi and you're dealing with trig, you should be in radians mode. Okay, so just a couple pieces of advice. The first one, let's just put this in our calculator. So we have cosine of 7 pi divided by 6, and it gives us this crazy answer. If you got that, it means you're wrong, because this calculator right now is not in radians mode. Let's give the same exact expression again. Equals, all right, it gives us a totally different answer. Negative root 3 over 2. So in this case, our answer is negative root 3 over 2. And if your calculator doesn't give that, you can also give its decimal version, which it actually asks for. It wants 2 decimal places, and now we've got 1, 2 decimal places. So we're okay. Nothing crazy going on here. I'd like you to try B and C now. I'm just going to write out the answers. So definitely give those a shot. Make sure you can get those. If you can't, try it again until you get it. And if you have an issue, let me know. For secant, we have a little bit of a situation going on, but nothing that we can't handle. Remember, secant's friend is cosine. It's the reciprocal of cosine. So we just take our expression, put it over cosine. And if you calculate that out correctly, you're going to get 1.08. So check that, make sure you can do it. If you can do it, then you know how to calculate the trigonometric values using a calculator. The next section that we're going to move into, it says we're going to be finding angles of theta in radians. So really the radians part is the trickiest part. Between 0 and 2 pi when values of trig functions are given. We've done this topic before. We already did this exact topic, but using angles in degrees. So let me write my little diagram out just as a reminder. And we can convert all of our main values to radians. I'll just do the most important ones, 0 and 180. Okay, now that we've got these relationships as a reminder, let's jump into page 12, which again, we've done these questions before. So let's get to it. When I say we've done it before, I'm going to say this topic is just like what we did on page 6. All right, so I recommend that you pause the video right now, go take a look at page 6 and see what I'm talking about. But it should become clear very quickly. We're looking for an angle between 0 and 2 pi. In fact, we're actually going to be looking for 2 angles. And so the first thing we're going to do is find the reference angle. But in this case, we're going to look for it in radians. So we know that cosine of our angle is 0.8387. The angle here must be cos inverse of 0.8387, which means that our angle, again, you must be in radians, is 0.576. That is our reference angle. If you remember what we did, or you're comfortable with what we did before, this is our reference angle, but in this case it's going to be radians, okay? Because that's the mode that our calculator is in. What's our second step going to be? Let me tidy this up. Okay, our second step, if you remember, we're still going to use cast to find 2 angles in radians. So I've set up my quadrants here. You can use cast, or you can say all students take calculus. And what do we do at this point? Maybe you forget. We need to look at the original function. The original function is cosine. Cosine's positive, and so we are dealing with quadrants 1 and 4. In quadrant 1, our angle we're looking for is just equal to the reference angle. So our angle is 0.576 radians. Sorry, I had a little bit of trouble with the pen there. And then we just need to get our angle from the 4th quadrant, because again, cosine's positive also in the 4th quadrant. Our formula in this case is normally 360 minus our reference angle alpha. The problem is we're not allowed to use 360 because that's a degree angle. So 360 is actually 2 pi, which is what I went through a little earlier. So 2 pi. 2 pi minus our reference angle. In this case, it's 2 pi minus 0.576 radians. Or in other words, our angle 2 is 5.707 radians. And I recommend that you check every single step of this so that you're clear why I'm doing what I'm doing, and make sure you can put in, 2 times pi in your calculator with no problems. By the way, you can use pi equals 3.14 if you want. That'll work just fine because of the precision we're looking for, but I recommend you use the digits on your calculator. In fact, that might not even be accurate enough to get us 3 decimal places. So I'm just going to say you can use it in a pinch, but I wouldn't recommend you use it in all cases. Okay, for sine, let's work out one more question where we do sine theta equals to a negative. Let's do the same steps as we did on page 6. First step, find reference angle in radians. I'm going to ignore the negative that I see because it makes no difference in terms of finding the reference angle. So there we go. We have our reference angle. I'm going to set up our cast process to find the angles. I'm dealing with sine. Sine is a negative in this case. Sine is negative in the 3rd and the 4th quadrants. That's because it's normally positive in the 1st and the 2nd quadrants. So our angle we're looking for is going to be in quadrant 3, and there's going to be another one in quadrant 4. Quadrant 3, our formula is usually 180 plus our alpha. In this case, we can't use 180 plus our reference angle in this case. We need to use pi plus alpha because pi is 180. So our first angle is going to be pi plus 1.045, or in other words, 4.187 radians. We'll continue the story here for quadrant 4. I recommend you pause the video and try to get this one yourself, but I'll write out my answer to this as well. And there we go. So those are the answers that I came up with for this question. I'm just going to rearrange. Just needed to make sure I had enough room on the page there. And I recommend now you pause the video, try questions C and D. You must try them yourself or you're never going to get better at them, okay? So I'm going to post the answers here in just a second, just as they are. I'm not going to go through them. And you make sure that if you have any trouble at all, you review them. And if you can't get it by reviewing, you let me know, okay? I'll post the answer right now. 3, 2, 1, and here they are. So pause the video, pick through my work if you need to. And again, please let me know if that doesn't make sense to you. Let's move on to the final section of today's video, which is dealing with arc length and the area of a sector of a circle. So before we get into the formulas for arc length and area of a sector, let me just show you what arc length means. Basically what it means is that if we have a circle, the arc length is how big the arc is. So this red part, I'm making it bigger, I'm making it smaller. This arc length would get bigger and bigger the more or the larger the angle is. So in this case, the arc length is, say, 1, and this is 2 and 3. Obviously, these numbers change based on the radius and everything else. But the bigger we go around the circle, the more we go out, the more we trace, the bigger the arc length. And if we go a whole 2 pi, we're going to get 2 pi r, which is actually the circumference. So in a way, we can say that the arc length is very much related to the circumference. In fact, it's a section of the circumference. So back to our notes here, the arc length of a circle is a fraction of the circumference, and the arc length of a complete circle is equal to the circumference. So what it's trying to say is to compare it to the circumference. But first of all, let me write out the formula. Arc length S is equal to our angle theta times the radius, and generally we're given this. So this would be a good reference formula. This is what we would use for arc length. I'm just drawing it big here so it can't be missed. All right, you can't miss it now. Arc length, this is our big formula. And it's mentioning the circumference here. It's saying really that we should compare this formula to C equals 2 pi r. Circumference equals 2 pi r. And that's because the circumference itself is related to 2 pi times r. 2 pi is just a full 360-degree turn. And so a full circumference would be taking this arc length and going around here 1 pi, 2 pi. We use our formula 2 pi times r, that is circumference. But you don't really need to know that in order to do this stuff. Just know that arc length is a fraction of the total circumference, and just use the formula. The area of a sector of a circle, a sector is a fraction of the area. So the whole area of this circle would be pi r squared. The sector is a fraction of pi r squared. So we can just say it's this little piece of the pizza there. Just like the arc length was the length of a certain arc, the sector, or the area of a sector, we take a section of the circle, and that's the area that we're dealing with. Maybe that's self-explanatory, but I wanted to mention it. So once again, the formula, 1 over 2 pi r squared. All of this is in radians, by the way, be careful. This is area of a sector of a circle. And what we should compare it to in this case is A equals pi r squared. Generally speaking, this is the area of a circle, and you should know that. We know it's area because it has these square units. So something I should mention is that the area of a section or a sector of a circle has units squared. For example, meter squared or kilometer squared or something like that. And once again, if we compare it to pi r squared, pi is 180 degrees. So it's a full half turn we would normally use. In this case, we're doing just half of an angle. Don't think about that too much. Just know this 1/2 theta r squared has something to do with this original pi r squared. But again, we don't need to get into the weeds with this one. You just need to know how to use the formula. So there's a couple notes. In this case, theta is known as the central angle, measurement from the x-axis or from somewhere. And then if the angle is given in degrees, make sure you convert to radians. That it couldn't be more important. You cannot use these formulas unless you're in radians. Okay? Just something to think about. Let's move ahead to page 14 and actually do a few practice problems. So the first question here, I'm actually going to leave for a second question. I'm going to do it next. The first one I'm going to do is this part B, example 1b. And let's see what it says. We'll zoom in so that it's not too much on the page. A circle, so we know it's a circle, has a radius of 15 meters. Find the arc length of a 135-degree sector. So I like to set these problems up by writing all of our given information. So the radius is 15. I'm going to include the units just in case. I need to find the arc length, which is s, and then I'm given the angle, which is 135 degrees. But I need to convert it to radians. So in order to convert that to radians, I need to multiply by what? Do you remember? It's 180 degrees on bottom, which will cancel the degrees out, and pi on top, pi radians on top. What this gives, if you multiply it, is 2.356. And now I've got my radians, okay? I want radians, not degrees. That's the most important piece of this question. The rest falls apart pretty easily. So if you know that you're dealing with arc length, just remember the formula for arc length, okay? It's theta times r, the central angle times r. You have both of those things. You just put in theta, theta being in radians. You put in the radius, radius being 15, and then the arc length is going to pop out of this. It's 35.3 meters. And we're all done. As long as we have radians, the units are going to take care of themselves. So the arc length here is 35.3 radians. If you work it out as with the pi still in there, technically it would be 45 pi over 4. Most students wouldn't get that. And it's not super helpful anyway, but just in case you wanted to know, that's something you can do. So I would like you to try example 1a. I'll leave example 1b there as a reference. I would like to see if you can get example 1a. The answer should be 106.3 centimeters. All right, so pause the video, give that a shot. I'm going to label things that we know. Find the length of an arc, so find the arc length. S, what is S? The radius of 24.73 centimeters. So the radius is 24.73 centimeters. And subtends, which means carries through or goes through a central angle of 4.30 radians. So the angle is quite thankfully already in radians. So in this case, no need to convert. Now all you need to do is use your formula. I'll write that out with no explanation. And here we go. This is our final answer, 106.3 centimeters. So you might be wondering, okay, I've got this, I worked this out. How did you know the units that you had to come out with? Well, it's very important that you know that we're dealing with length, and look to your question for the units. In this case, our radius was given in centimeters, and so they're going to match in the end. So some piece of advice here is look to the original question for the units. Okay, and then if you can handle that, you should be fine. Let's take a look at the last question in this section on arc length. See if we can handle this question. A circular sector, so again it's a circle, central angle of 165, arc length of 25 meters, find the radius. So in this case we're looking for radius. We're looking for something a little different this time. So we can go about this a couple different ways. Let's start with the formula. And let's rearrange the formula, or should I say, let's try putting in the numbers right away as I see them. So I've substituted all my values in. I knew S, I knew theta, and this is now a pretty easy problem to solve. I just divide by 2.88 on both sides, and that will give me radius. And that's it, that's my answer. That's one approach. There is an alternate way you can do this question. So I recommend, if you're good at transposing equation, is that you solve for your r first. So you know you're looking for r. So if you rearrange this formula, which is really just dividing both sides by theta to get r on its own, r is equal to the arc length divided by theta. And now you can substitute your values in and get your answer. And there we go. Same exact answer. Makes no difference which way you choose. I recommend you choose the method that's easiest for you. We have one more topic to cover, which is the area of the sectors, which is done a very similar way to this one, to what we did for the arc length. So in example 2a, it asks to find the area of the sector of a circle. Okay, good, it's a circle, with our radius equal to 49.4 centimeters and our angle being pi over 12 radians. So we're looking for area. I'm going to write what I've been given. So at this point, you don't need to keep the pi. You could actually change it into its accompanying decimal, but just for the sake of argument, I'm going to keep it the way it is until I have to calculate using it. So our area formula, just go and check the other page a couple pages ago, we know our area is this. And if you forget it, remember the area of a full circle is pi r squared. All you need to do is change out this pi with something, and then in this case it's 1 over 2 theta. Just something to remind you which one's which. So just substitute all your values in, and you'll get your answer. So this is my answer. I'm going to even put it in a box to show that I'm done. The problem is, this is an area. The area needs to have units. You can't just have, especially if you're given centimeters, we can't just call it 319.4. If you're trying to build something, you want to know if it's meters, kilometers, centimeters, millimeters, how big is it? And it turns out we're going to match the units that we started with, but make sure that you add in a square to make sure that you're giving square units. So you need to remember, area always has squared units. Okay? And for those of you that carried the pi through all the way to the end, there is an alternate answer for this, which I'll write here. And there you have it. So that's how you do area of a sector when you're given all the information. I recommend now that you try to do question B. If you do question B correctly, you should get an answer of 1413.7 meters squared. So pause the video, give that a shot, see what you get. I'm going to write down my answer and you can compare it to that. So notice for this question, I know that it's area. I was given units in meters, and so my final answer needs to be given meters squared. Just like in the previous question, we did the same thing with centimeters squared. Always square units with always square units with area. Let's move on to the very last question we're going to do in this video, which is the area of a sector is 18.8 meters squared. So we're given area this time. And the radius is 7.71 meters. Find the central angle in radians and degrees. Okay, interesting. We're going to have to get a final answer here in two different ways. So the formula will give us an answer in radians, and we're just going to have to convert at the end. So what's our question? Our question is to solve for the central angle. So first thing we're going to do, let's write out our formula. And then we want to make sure that we can get our answer as a theta. So most students find it easier to put our numbers in first. So let's do that. So I'm going to keep the left side the way it is, and I'm going to multiply all the numbers on the right side. So that's 0.5 times 7.71 squared gives me 29.72205. I decided to keep all the digits here because there's not that many, and maybe they'll be useful later. Divide by that, and we get our answer. Now you need to know that at this point, because this formula uses radians, you're going to get an answer here in radians. Remember that, again, the formula used only deals with radians, always. So this is our radians answer. Now, if we want our degrees answer, we should convert it. So we know that our angle is 0.633 radians. So we just need to multiply by the conversion factor. We know that we can multiply by 180 degrees over pi radians. That will then cancel radians from top and bottom, and in the end we're going to be left with our degree answer. So that conversion works just the way that it did earlier. And if you work that out, you get 36.3. All right, and that's it. That's the whole answer for this question. That's our degrees answer. So we've got our radians answer, we've got our degrees answer. You can stop the video right here, but I recommend that you take one quick look at an alternate way you could have done this question. Instead of substituting first, we'll rearrange first. Some students prefer this. Remember, we're looking for theta, so let's rearrange this formula for theta. And if we get that answer, if you work that out and you're okay with that, you can substitute your values now and get the same answer as we got previously. And there you go. No matter what way you slice it, you can get that answer in radians. So that's it for today's lesson. Hopefully you learned something. Hopefully you're not too confused. If you need any help, I'll say it again. I feel like a broken record, but if you need help, please just contact me. I'm happy to go through this anytime you like. All the best with it, and I'll see you in the next class.